December 7, 1941. Pearl Harbor burns, and within 72 hours de Taidan Foni de Dinsaraltoi 2 hours, the United States military faces a logistics nightmare that has nothing to do with battleships or aircraft. Across the Pacific Theater, from the Philippines to Wake Island, American forces are sleeping in canvas tents that fall apart under heavy tropical rain within just 3 weeks. The War Department's morning reports become serious when messages arrive from the field telling how entire supply depots are flooded, ammunition destroyed, and soldiers sent to hospitals with pneumonia because their shelters literally came apart during the monsoon season. Wooden barracks need skilled carpenters, weeks of work, and lumber that just doesn't exist on small coral islands. The Navy figures it would take about 18 months to build regular housing for the troops they must send right away. In Washington, Brigadier General Eugene Raybould stands before a table covered with weather charts and construction schedules. His engineers face an impossible problem. They need buildings that can be made fast in Pennsylvania, shipped 10,000 miles through waters full of enemy submarines, put together by tired Marines who have never even held a wrench, and still stand strong through everything the Pacific can bring. That means burning heat of 130 degrees, massive typhoon winds, monsoons that drop 15 inches of rain in only 6 hours, and the real chance of Japanese bombing runs. The regular Army tent costs $12, but lasts 1 month in jungle conditions. A wooden barracks building costs $8,000 and needs a crew to build for 6 weeks. Neither choice works when you are jumping from island to island across the Pacific and need shelter for 50,000 men right now. The British have been fighting longer, and their experience in North Africa gives a hint. Since 1916, they have used Nissen huts, half-round steel shelters made by Canadian engineer Peter Nissen during World War I. These metal half-circles can hold 30 soldiers, need no skilled workers to put up, and can stand strong against sandstorms. But the Nissen design has big problems for the Pacific. The British version uses heavy steel parts that need special lifting tools. The air system works fine in the Libyan desert, but turns the inside into a hot oven in the Philippine heat. Worse, each hut needs custom base work, which means pouring concrete or building wooden floors, and that brings you right back to needing carpenters again. Raybould's team figures they need housing for 2 million people spread over hundreds of islands and bases. The math is harsh. At normal building speeds, the war would finish before half the soldiers had roofs over their heads. Troops are already writing home saying they wake up with boots full of rainwater, that fungus grows on their clothes overnight, and that the tents fall down during storms and leave men crawling in the mud at 3 in the morning. The medical team says lung sickness is putting more men in hospitals than the enemy is in some places. This is not just about comfort. It is about keeping a fighting force from breaking down before battle. The message goes out to American builders, college research labs, and the Navy's own building units. The design request sounds like something out of science fiction. Create a shelter that weighs less than a Jeep, fits on one rail car, needs no base, and can be put together fast, in 1 day with simple tools, costs less than $1,000, and survives weather that destroys even solid buildings. Oh, and have 10,000 ready to ship in just 6 months. It is February 1942, and somewhere in Rhode Island, a group of engineers is about to turn an impossible idea into real life. The Nissen hut plans arrive at the Navy's Bureau of Yards and Docks in an unusual act of wartime teamwork. British engineers, thankful for American supply help, share detailed blueprints of their World War I shelter design. 16 feet wide, half-circle tunnels made of corrugated iron sheets bolted to a wooden frame. Commander John Philip Drosfeld studies the papers and right away sees both brilliance and trouble. The smart part, the arch shape naturally pushes away wind and lets rain slide off without any fancy design work. The trouble, a long list of issues that would ruin the huts in the Pacific. The British huts weigh 3 tons when taken apart, need foundation bolts drilled into concrete, and have a wooden frame inside that becomes food for termites in hot, wet climates. Drosfeld circles the air vent design in red pen. 2 small windows built for cold Scottish weather would turn these huts into burning ovens in Guadalcanal's 98-degree heat. Average temperature. But there is another American voice in this story, and it comes from a very unexpected place. Buckminster Fuller has been talking about factory-made homes since the 1920s, though most architects think he is just strange. His Dymaxion house idea, built in a factory, lightweight, and put together on site, sounds almost like a prediction. In 1942, Fuller's ideas about making houses like cars, using industrial materials instead of wood, and designing them to go up fast, all start to sound less crazy when the nation must build a whole city's worth of housing every single month. The military has not spoken with Fuller directly, but his published writings are moving through engineering schools, and his main idea becomes priceless. Treat buildings as products that are made, not as long construction jobs. The Navy brings this kind of thinking together at their base in Quonset Point, Rhode Island, a newly opened air station on Narragansett Bay. The location is not by chance. Rhode Island has deep experience working with sheet metal from its jewelry and silverware factories. Plus, it is close to steel mills in Pennsylvania and shipyards that already understand how to fight off rust in sea air. In March 1942, the Navy gathers a special group, structure experts from the Strand Steel Corporation, who make prefabricated farm buildings, architects from the George A. Fuller Construction Company who know fast building methods, and Navy officers who have actually served in the Pacific and know what stormproof really means compared to what it sounds like on paper. The team leader, Otto Brandenberger, brings farm building experience that turns out to be just right for this challenge. His Strand steel barns use curved metal panels that support themselves. No inside frame is needed, which means no wood for termites to eat and no tricky joints to fail in strong storms. Brandenberger's bold idea is to remove the Nissen hut's wooden frame completely and make the corrugated steel shell hold all the weight. This breaks the normal building rules of 1942, when steel is used for bridges and tall buildings, not for self-supporting shelters. But Brandenberger knows his barns have already stood through Midwest tornadoes without inner frames, and he is ready to prove the same idea can work on a larger scale. The British add another key piece through their hard lessons. Their Nissen huts in Burma and Singapore have shown exactly how tropical weather destroys buildings. Mold is not just ugly. It actually eats through wood coatings and paint in a few months. Moist air does more than make things wet. It rusts metal bolts until roofs cave in. Bugs are not just pests. Carpenter ants can turn wooden beams into hollow shells in one season. The British reports sound like horror stories, but they give the Quonset team a list of everything that must be designed out of the structure from the very start. No wood touching the ground. All steel must be hot-dip galvanized, never just painted. Airflow must be strong enough to stop moisture buildup. Every bolt must be easy to replace without taking the whole hut apart. By April 1942, the combined idea becomes clear. Use the Nissen hut's smart arch shape. Remove everything heavy or weak. Add Fuller's factory building method and American steel strength. And design every part for the brutal reality of Pacific Island warfare. April 15, 1942. Otto Brandenberger walks into a Quonset Point warehouse with 30 engineers and a deadline that would be funny if the war were not so serious. 60 days to design, build, test, and approve a brand new kind of building that doesn't even exist yet. The team works in shifts non-stop, sleeping on cots pushed against the walls, living on Navy mess hall coffee, and the kind of stress that either creates genius or total burnout. Brandenberger splits his team into small groups. One handles airflow and structural strength. Another figures out how to pack parts together for shipping. A third works only on fixing the joint and bolt. Problems that hurt the British design. The first bold choice happens on day 3. Normal building drawings take weeks, and they don't have that long. So they build in real time, sketch a part in the morning, have the metal shop make it by afternoon, test it overnight, and fix it by morning. This build, test, repeat method is common in 2025, but was shocking in 1942 when most buildings were fully planned on paper before cutting any material. The warehouse floor turns into a lab filled with broken joint tests, bent metal panels, and better versions of each piece. The engineers borrow a trick from airplane factories. Every single part gets a number, every update gets recorded, and nothing moves to the next version until the last problem is solved. The size choices come from tough, simple math, not looks. 16 feet wide, the biggest size that fits on a regular rail car without needing special shipping permits. 20 feet long per section, so it can be handled by small work crews without cranes or extra machines. Section, short enough that 4 men can lift one panel, but long enough to make useful space inside. 48 feet total when built, it can hold 36 men with beds, or be changed into offices, medical areas, or storage rooms. The Quonset team finds that this size hits the perfect balance in building strength. Make it smaller and you waste shipping space. Make it bigger and the panels get too heavy to build by hand. Or the curve needs inside supports that bring back all the same problems they are trying to avoid. Figuring out the right curve takes 2 full weeks of their 60-day deadline. 2 flat and strong winds could rip the hut open like a can of sardines. Too steep and you lose space inside and create hard shapes for the end walls. Brandenburger's group decides on an 8-foot curve, a perfect half circle that gives 7 feet of headroom at the sides and forms what engineers call a self-bracing arch. The wavy steel naturally wants to stay in that curve, which means the metal can be thinner and lighter while still being strong. They do math tests showing the design can handle snow loads up to 40 pounds per square foot and wind speeds over 100 miles per hour. But numbers on paper and real Pacific storms are 2 different things. By day 40, they finally have something that might really work. A rough mix of riveted panels, test joints, and borrowed bolts. The first full prototype is built on May 25, 1942, put together by 6 sailors who got 4 hours of lessons and only simple hand tools. The total time to finish it is 14 hours, which is good news, but still not fast enough. The Navy wants the huts to be built in one single day, because marine landing plans don't allow time for projects that take several days. The team spots the problem right away: the floor system. They had been trying to include a wooden floor as part of the kit, but it takes the longest to put together and is also the first thing to rot in the hot, wet climates. The answer is smart and simple. Take the floor out of the main design completely. The hut sits right on whatever ground is there: coral, sand, dirt, or, if lucky, gravel. When a solid floor is needed, it can be added later as a separate job. But the main shelter now gives full weather protection without it. This one change cuts build time to 8 hours and lowers shipping weight by 1,200 pounds per hut. On June 10, 1942, the final test model stands finished. 96 corrugated steel panels, each weighing less than 50 pounds, bolt together to form 720 square feet of closed space. Total materials cost $1,394. Total weight 9,000 pounds. The real test begins next. Second layer of genius. Those ridges running along its length make the structure much stronger, like how folding a sheet of paper makes it stiffer than when it's flat. Each corrugation works like a tiny I-beam, stopping bending forces that would crush smooth steel. The math gets really interesting when you look at how weight and pressure move through the arch. In a normal box-shaped building, the roof presses down on the walls press down on the foundation, and the whole thing depends on those vertical paths staying solid. Storm winds can literally rip the roof off since it just sits on top of the walls. The Quonset arch changes that completely. It's one smooth curve where every panel shares the load with the others. Engineers call this a compression ring. The the same idea that lets stone bridges stand for hundreds of years without mortar. The hoop stress, or sideways pull trying to spread the arch apart, is handled by the ground itself. Each Quonset panel bolts to the next one, with 3/4-inch steel bolts spaced every 6 inches, forming what's basically a 48-foot-long steel cable shaped into an arch. But no amount of math matters without proof. So the Navy sets up tests that border on cruel. They build a full-scale Quonset at Davisville, Rhode Island, and cover it with strain gauges, pressure sensors, and deflection meters. Then they wait for the first big nor'easter. On March 3, 1943, a storm hits with 75-mile-per-hour winds and heavy snow. Perfect test weather. The instruments show the building bending less than 2 inches at the top, then springing right back once the wind dies. The joints hold, no leaks. The hut performs exactly as the math said it would, which is both exciting and a little scary since they're about to trust thousands of lives to this design. Testing in tropical weather turns out trickier than wind. You can't copy years of jungle heat and moisture in a Rhode Island warehouse. So the Navy sends a test hut to the Panama Canal zone, where it's 80+ degrees and 85% humidity year-round. 6 months later, the report comes back. Only slight rust on the galvanized panels, no damage to the frame, but major trouble with condensation inside. When warm, damp air hits the cooler steel at night, it rains from the ceiling. The fix is to add vent openings at both ends and along the top ridge, to let hot air escape and keep airflow moving without losing strength or weatherproofing. These vents raise the cost by $47 per hut, but turn it from a metal oven into something people can actually live in under tropical heat. The last engineering hurdle is the A question is how to anchor a 9,000-pound building to loose sand or coral without pouring concrete. The answer borrows from tent No How Scaled Up. Heavy steel stakes driven into the ground and tied to the hut base with adjustable tension cables. For harder ground, the team makes a bolt pattern so the hut can fasten directly to wooden sleepers or pierced steel planking. The great thing about this system is its forgiveness. The building can move a little with ground shifts and not rip itself apart. In June 1942, the War Production Board approves Quonset hut manufacturing. And what follows is American industry at full speed. The Navy signs contracts with 10 major steel fabricators across the Midwest and Northeast, companies that were making grain silos and water tanks 6 months earlier and are now retooling to build military shelters. Strand Steel converts its Penrose plant outside Philadelphia to Quonset production. George A. Fuller Construction takes over an auto parts factory in Chicago. Great Lakes Steel assigns 2 rolling mills to nothing but corrugated panel making. By August, these factories are producing 1,500 complete huts per week, and the output keeps rising. The manufacturing borrows heavily from auto assembly line methods. Massive steel coils arrive by rail. Each coil is 4 feet wide and holds enough steel for 30 panels. Rolling machines press the flat steel into shape, forming those strength ridges spaced exactly 2.67 inches apart. This corrugating stepwork hardens the metal, making it tougher than the sheet that entered. Then the panels move through galvanizing tanks and get dipped in molten zinc at 850 degrees Fahrenheit. This zinc coat isn't paint. It bonds with the steel and protects it by corroding first. In salty Pacific air, that layer means the difference between a 5-year life and a 50-year life. The step adds $112 to each hut, but becomes mandatory after reports show ungalvanized steel rusting through in 8 months. Every complete hut kit gets packed with careful attention to shipping details. The 96 corrugated panels nest together like stacked bowls, cutting the bundle height from 8 feet to just 14 inches. The end walls, plywood sheets with pre-cut door and window openings, fit flat between the steel panels. All bolts, nuts, and other hardware go into one wooden crate that includes illustrated instructions meant for men who may not read English well. The full kit loads neatly on one standard 40-foot flatbed rail car. This packing efficiency matters because every train heading to West Coast ports hauls either Quonset huts, ammo, food, or vehicles. There's zero space for wasted cargo. The transport rhythm runs like clockwork. Trains roll out of Philadelphia and Chicago every day, bound for San Francisco, San Diego, and Seattle, where Liberty ships and other cargo vessels wait at dock. Longshoremen load full hut kits into ship holds using the same cranes built for tanks and guns. One Liberty ship can haul 200 Quonset huts with their hardware, enough shelter for 7,200 men. The War Shipping Administration logs every load because these aren't just buildings, they're vital assets. A hut shipped to Guadalcanal in September might house a bomber crew by October, meaning the difference between working planes and pilots sleeping in mud. The assembly phase on arrival is where the Quonset's brilliance truly shows. The Navy's construction battalions, the famous Seabees, create exact methods that turn setup into a precise, repeatable task. 6-man team, 8 hours later, one finished hut stands ready for use. The process begins with site prep. Level the ground, clear plants, spread gravel if available. 2 men handle the end walls while 4 manage the curved steel panels. Each overlaps by 6 inches and bolts together with sturdy 3/4-inch fasteners. No welding, no concrete, no skilled labor, just wrenches, a level, and simple illustrated directions. The record goes down on Espiritu Santo in January 1943 when a specially trained Seabee team assembles a full hut in 4 hours and 17 minutes. That's showing off. But the real success is steady output across hundreds of islands where crews raise 5 or 6 huts daily, building entire bases faster than the enemy can bomb them apart. By December 1943, monthly output climbs to 8,000 units. The supply chain runs so smoothly that huts made in Pennsylvania reach New Guinea within 40 days, including the ocean trip and Pacific offload. The cost math seals the win. Each Quonset shelters 36 men for $1,394 in materials and around 60 man-hours of work. Compare that to standard barracks, $12,000, 400 man-hours, and 6 weeks to build. The Quonset gives housing at 1/10 the cost and 1/20th the time. By mid-1944, the U.S. military has shipped more than 160,000 units to every war zone, enough shelter for nearly 6 million troops built in under 2 years. Guadalcanal, August 1942, the first combat Quonsets land on a beach at 95 degrees, 90% humidity, while Japanese bombers attack daily. Marine engineers unload the flat-packed panels under shell fire and start bolting them together among the coconut trees, still showing scorch marks from last week's shelling. Within 12 hours, Henderson Field has 10 new huts housing maintenance crews for the battered F-4F Wildcats flying from the airstrip. The true test comes 3 days later, when a Japanese bombing run scores a near hit. A 500-pound bomb explodes 40 yards from a hut full of aviation mechanics. The blast flattens nearby palm trees and tears canvas tents to pieces. But the Quonset bends and holds. Dirt and shrapnel bounce off the corrugated steel. When the smoke clears, the hut is standing, with every man inside shaken but alive. The jungle itself is as tough as enemy fire. Within 2 weeks, red rust streaks appear on any ungalvanized bolts. Salt air eats through normal hardware like acid. Mold grows wherever moisture collects, turning walls into strange black and green patterns. The ventilation louvers that worked in Rhode Island barely move the thick, humid air. Marines start keeping doors propped open all the time and cut extra vent holes with tin snips, breaking the original rules but making the huts livable. These field fixes are recorded and sent back to Quonset Point, where engineers add them to new production. More ventilation, bigger louvers, and every fastener fully galvanized, no matter where it goes. Iwo Jima, February 1945. The volcanic island brings a whole new kind of hell. Black sand blows into every crack. There's no topsoil to hold stakes, and artillery from Mount Suribachi constantly threatens. Seabees arrive on D-Day +2 and start putting up Quonset huts under fire, literally bolting panels together while mortar rounds land 200 yards away. The volcanic sand makes normal stakes useless. Crews improvise by filling empty oil drums with sand and tying them to the hut bases with cables. When a Pacific typhoon hits in March with 110-mile-per-hour winds, these makeshift anchors hold, while wooden buildings across the island fall apart. The base commander's report back to Pearl Harbor is simple. Quonset hut survived. Everything else destroyed. The Arctic tests the huts in the opposite extreme. Alaska's Aleutian Islands campaign uses Quonset huts at Dutch Harbor and Adiak, where temperatures drop to -40 and winds often top 100 miles per hour. The cold makes steel brittle, and early huts crack around bolt holes. Engineers fix this by using cold-rolled steel with a different metal mix for Arctic missions and adding rubber gaskets at every joint to keep the huts flexible. Heating the huts causes new problems. Warm air hitting frozen steel creates condensation that literally rains inside until crews figure out to install insulation blankets and run ventilation even in sub-zero weather. By winter 1943, weatherproof Quonset models have internal insulation batting, double wall construction for extreme cold, and updated ventilation systems that keep heat in while controlling moisture. North Africa and Italy present completely different challenges. At Palermo, Sicily, a Quonset hut used as an ammo depot takes a direct hit from a German 88mm artillery shell. The shell pierces the steel, explodes among crates of ammunition, and should destroy the building. Instead, the arch shape spreads the blast outward through walls and roof, leaving the frame twisted but standing. EOD crews studying the wreck note that a rectangular building would have collapsed, burying anyone inside under tons of rubble. The arch's natural strength, the compression ring effect, means even huge damage doesn't make the building fail completely. The Pacific typhoon season of 1944 gives the ultimate test. Super Typhoon Cobra hits the Philippines in December with winds up to 140 mph and a 20-foot storm surge. At Tacloban, the storm wipes out 80% of all base buildings. Wooden structures splinter. Concrete block buildings collapse when winds undermine their foundations. But of 43 Quonset huts on the base, 39 stay fully intact, and 4 suffer only repairable damage. Panels bend, seams tear, but none fail completely. Engineers studying the surviving huts find that proper anchoring matters more than anything else. Huts with strong ground attachments survive the storm. Those with weak or makeshift anchors roll away like tumbleweeds. By the end of the war, performance data from 50 combat zones feeds continuous design improvements. The 1945 production models look very different from the 1942 prototypes. Better ventilation, stronger bolts, improved insulation, and field-tested fixes turn a good design into an excellent one. May 8, 1945, victory in Europe. August 15, 1945, victory over Japan. Suddenly, the U.S. military has about 170,000 Quonset huts across 6 continents and no clear plan for them. The original idea was that these were temporary wartime shelters to be scrapped or abandoned once permanent buildings could be built. But something unexpected happens. No one wants to get rid of them. At hundreds of bases set for closure or downsizing, commanders see the Quonset huts not as old wartime relics, but as fully functional buildings that cost almost nothing to maintain and can be used for nearly anything. The War Assets Administration, responsible for selling off extra military property, faces a strange problem. There are more people wanting used Quonset huts than available huts to sell. Returning veterans find a housing crisis so bad that families live in converted chicken coops or share apartments with 3 other families. The building industry, starved for materials and workers during 4 years of war, can't keep up. Into this mess steps the Quonset hut, now for sale to civilians at bargain prices, $1,000 to $2,500 for a complete hut that would cost $8,000 to build, normally, if you could even find builders. The federal government pushes this repurposing, giving veterans priority for Quonset purchases. By late 1946, entire suburban neighborhoods of Quonset huts appear around major cities. Roger Young Village in Los Angeles houses 750 families in converted military huts. Vetville developments pop up near universities, where the GI Bill is sending thousands of students to campus who need housing fast. People get creative with the huts. Families add wooden facades to the curved ends, making them look less like military surplus and more like fun cottages. Inside, walls divide the space into bedrooms, living rooms, and kitchens. Windows are cut into the steel sides, breaking structural rules but making the huts truly livable for family life. Some owners take it further, burying huts halfway into the ground for natural insulation or connecting several huts end-to-end to make larger compound homes. Housing inspectors and building officials hesitate to approve these changes, but the housing shortage is so severe that cities reluctantly grant permits. In Portland, Oregon, a whole neighborhood called Fairview Addition has 350 Quonset homes. Residents plant gardens, paint the steel walls bright colors, and add normal-looking porches to hide the military origins. Churches find Quonset huts solve another problem, providing space for growing suburban congregations without the long, decade-long fundraising campaigns traditional church buildings need. First Presbyterian Church in Levittown, Pennsylvania, holds services in a Quonset hut from 1952 until 1967, when they finally raise enough money for a permanent sanctuary. Many other congregations make the same choice. $2,500 for instant space beats $150,000 for future grandeur. The sound isn't great, the look is plain, but people can worship next month instead of next decade. Some of these temporary church huts stay in use for 30 years, outlasting the first generation who saw them as short-term solutions. Schools adopt the huts too. Post-war enrollment booms with the baby boom, and school districts face the same impossible math the military faced in 1942. They need classrooms fast, but traditional schools take years to build. Rural districts especially use Quonset classrooms. One hut holds 30 students at 1/10 the cost of a regular school. By 1950, an estimated 3,000 schools across the United States include at least one Quonset hut classroom. Some students spend their entire elementary years in these steel tunnels, learning multiplication and history under curved ceilings that once sheltered B-29 crews in the Pacific. The commercial sector gets involved too. Small businesses, machine shops, auto repair garages, warehouses, and farm storage find Quonset huts, provide open space without internal support columns, perfect for industrial work. A welder can set up shop in a surplus hut for less than 2 months' rent in regular commercial space. Farmers adopt them eagerly. Strand Steel Corporation, which helped design military Quonsets, returns to make civilian versions for agricultural use. Thousands of Midwestern farms add Quonset buildings for grain, equipment, and livestock. Maintenance is simple. Hose off the outside once a year, check the bolts sometimes, and the hut lasts indefinitely. This civilian use creates an accidental architectural legacy. Quonset huts become part of American visual culture, symbolizing practicality over pretense, function over form, and making do ingenuity. They appear in movies, TV shows, and photos as shorthand for post-war optimism mixed with austerity. Architects once dismissed them as temporary eyesores, but by the 1990s, preservationists recognized surviving Quonset huts as important examples of adaptive reuse and vernacular architecture. Several even earn historic landmark status, are protected as symbols of a unique moment when military technology successfully moved into civilian life. Modern disaster zones show why Quonset hut design keeps reappearing in 21st century emergency response. After the 2010 Haiti earthquake destroyed Port-au-Prince, relief groups face the same problem American military planners faced in 1942. Immediate shelter for hundreds of thousands of people, no infrastructure, no time for normal construction, and conditions that destroy weak temporary housing in months. The solution borrows directly from Quonset principles, even if designers don't know they're using 1940s military engineering. Arched steel frames, corrugated metal panels, prefabricated parts that ship flat and go up fast. The basic idea hasn't changed because the physics and logistics haven't changed. The United Nations High Commissioner for Refugees now uses shelters called RHUs, Refugee Housing Units, which are basically Quonset huts with 80 years of material improvements. Instead of corrugated steel, they use insulated composite panels. Instead of bolts, they snap together. But the core concept is the same: curved shape for strength and wind resistance, self-supporting arch, no internal framing, flat pack shipping. Massive numbers reach remote areas and assembly by unskilled workers with minimal tools. 2 people can set up a modern RHU in 4 hours, almost exactly like a 1942 Quonset. Today, these units shelter over 200,000 displaced people in camps across Africa, the Middle East, and Asia. Hurricane-resistant construction has rediscovered arch shapes after decades of rectangular buildings that storms destroy. After Hurricane Katrina hit the Gulf Coast in 2005, engineers saw that curved buildings survived while whole neighborhoods of rectangular homes were flattened to foundations. This led to research in aerodynamic architecture, designing buildings that work with wind instead of fighting it with brute force. The result looks a lot like a Quonset hut because the physics hasn't changed. Wind flowing over a curve creates less pressure than wind hitting a flat wall. Today, just like in 1942, the modern tiny house movement unknowingly rediscover Quonset principles when designers try to get the most interior space using the least materials and cost. Today, several companies make arch-roofed prefab cabins using the same corrugated metal and self-supporting curve that Otto Brandenburger first created. These cabins sell to people wanting affordable housing, disaster-resistant buildings, or off-grid living. Marketing focuses on sustainability and modern style, rarely noting that the basic architecture comes from a World War II military shelter. Some luxury architects have reimagined the look, adding floor-to-ceiling glass walls and high-end finishes costing $300 per square foot, while keeping the signature curved shape. The arch has gone from practical need to design statement. Military use never really stopped. The U.S. Armed Forces still deploy arch-style shelters in conflict zones. Afghanistan, Iraq, and secret locations all have modern descendants of the original Quonset. Current military designs call for shelters that can be lifted by helicopter to mountain bases, assembled under combat conditions, and survive IED blasts. Materials have improved. Aluminum alloy frames, Kevlar reinforced panels, and climate control systems. Show a 2025 deployable shelter to the 1942 Quonset engineers, and they would immediately recognize their own design ideas. Recent innovations include expandable units that unfold from shipping containers like origami and lock into rigid arches in an hour. The economic argument that justified Quonsets in 1942 still holds. When disaster strikes or rapid deployment is needed, conventional construction can't compete on speed or cost. A modern engineered arch shelter provides weather protection for about $50 per square foot, including shipping and setup. Regular construction in the same locations costs $150 to $300 per square foot, and takes months if contractors are even available. For humanitarian groups and military logistics managing huge budgets, this difference matters a lot. The math that drove Quonset development. how to shelter the most people with the least money in the shortest time, hasn't changed because scarcity economics haven't changed. Perhaps the ultimate proof comes from space exploration. NASA and private space companies designing Mars habitats keep arriving at Quonset-like solutions. Proposed Martian shelters have arched shapes to withstand severe dust storms, prefabricated parts that ship on spacecraft, and self-supporting structures needing minimal foundations. On Mars, the challenges of extreme environments, limited tools, unskilled assembly, and maximizing strength from minimal materials mirror the Pacific Theater of 1942 so closely that engineers independently rediscover the same solutions. When humans finally build permanent shelters on another planet, there's a good chance their design heritage will trace back to 30 engineers working in a Rhode Island warehouse during the darkest days of World War II. 13 typhoons, solving an impossible problem with corrugated steel and brilliant simplicity.